All right, so everyone, please welcome Jiannan from Snarkify.
Thank you for the intro, Alex, and thanks for everyone for being here. Today I'm going to be talking about our work on porting zPrize top optimizations to the MINA prover. The result is a library. We call it ArcMSM. It's a MSM implementation on Arkworks. A little bit about myself. So I'm a PhD in operating systems, specializing in HPC and cloud computing, a former Facebook research scientist. From 2018, I started to work on GPU and FPGA-based crypto mining, so I have years of experience on GPU and FPGA acceleration. Starting from last year, we pivoted to ZKP and start building Snarkify. Our vision is to trying to scale out the ZK infra. So on building large-scale proof systems for the decentralized future as well as ZK applications. I'm also an NFT collector. Okay, about the background of the problem we are solving. So we are porting zPrize results to Arkworks. So zPrize, as you may already know, is open source ZK hardware acceleration competition. It has two problems mainly. One is MSM, one is NTT. MSM, as I will talk more about later, has tracks on WASM, which is run in your browser, on mobile, on GPU, and on FPGAs. In this work, we focus on the WASM side because we focus on the CPU implementation. Especially in this work, I'm more focusing on the algorithmic optimizations, which is generic. So it works on WASM, it works on x86 as well. So it's, you can run it on your native environment, not just your browsers. And we use BIS 12381 in this talk. Our goal is to import the top optimizations to Arkworks used for MINA. Okay, about the MSM problem. Basically, it's a vector, is a dot product of two vectors, one scalar vector and one point vector on the elliptic curve. So for our work, the scalar is 255-bit, while the point has two coordinates. Both of them are 381-bit field. The input size can be up to millions. Okay, this is a Pippenger algorithm that's used in the baseline, as well as almost all the implementations of MSM, including CPU, GPU, and FPGAs. So the idea of the Pippenger algorithm is to divide those K into multiple partitions. We call it multiple windows. So you can treat this as K0, K1, K2. And then you, depends on the value of the K, you put it into different buckets. So for here, the K, you divide it into 4 bits windows. So you need 2 to the 4, which is 16 buckets. However, you do not need bucket 0, because 0 multiplied the point is still 0, so you don't need that bucket. Then you depend on this value, you put the points into different buckets. For example, this one is here, 14, then the other one are all put in this bucket. Then you add those points in the same bucket together. And then you add the buckets together with weight. So you can see that G0 is I minus multiplied with BI, then add them together. This is the idea of the Pippenger algorithm, and this visualization is from PipeZK. So with an example, more concrete example, if we are going to calculate this MSM problem, depends on the factor of the scalar of this point. You divide those into multiple buckets, and then add this bucket together, and finally, you get the final result P. And we call this procedure bucket accumulation because you are adding the points in the same bucket together. And we call this procedure bucket reduction because you are adding the final value of different buckets and reduce them to one result. As you can see, in this example, we reduce the number of multiplications from 8 to 4. That's the idea of Pippenger. I need to emphasize that our optimizations are built on top of this baseline. So the baseline is already fairly fast, but we achieved even more performance improvement on top of this baseline. So about performances. First of all, I need to acknowledge all the contributors. First of all, zPrize. Without this open competition initiative, there won't be those much high-performance source code and algorithms out there for us to use. I'd also like to thank Neil Alma from the Read Software, who is the first place winner, as well as Gregor from O1 Labs, who is the second place winner. Both of them have their code open sourced and give us a lot of technical guidance on this project. And finally, this implementation is funded by a MINA grant. Okay, those are all the techniques we implemented. As you can see, the first place and the second place winners pretty much implement the same techniques. On top of the baseline, they implement around 5 optimization techniques. Well, in this work, in my talk, we implement all these 4. For the last one is WASM specific. Basically, you change the big integer representation in the field. Instead of using the default 32-bit NIM, or on x86 it could be 64 NIM size, we use 30-bit NIM size for WASM because WASM instructions does not support certain properties, especially to handle the carries. For other implementations, we have other 4 tricks. The first one is to use batch addition of affine points in bucket accumulation, I mentioned before. The second one is treat the bucket indexes as signed integers. The third one is to use batch addition again in the bucket reduction step. And the final one is use a technique called GLV Decomposition. So without further ado, I'm thrilled to introduce that we have achieved over up to 2x performance improvement on a single-threaded speedup over Arkworks on x86 CPUs. Here is a graph of the detailed performance improvement. So the x-axis is the input size, range from 2 to the 8 to 2 to the 18. And the y-axis is a speedup result. Each column, each color is an optimization. You can see from the baseline with one optimization technique and 2, 3, and all of them, we achieve different performance results. As you can see, there's little or almost no regression when we apply one optimization on top of the other. Each time we achieve some kind of performance improvement, and overall, our final result is from 1.6 times faster to 2 times faster. That's the result we got. And I'm going to talk a little bit more about the algorithms and optimizations we used. First of all, the basic one, batch addition, we use it twice. I will discuss why it works. So here is how the equations, how do you calculate 2 points with affine coordinates. You first need to calculate the k, which is delta y divided by delta x. Then with this k, you can calculate the final xr and yr. This inversion is very expensive. It's over 100 times more expensive than the multiplications here. So that's why we want to amortize this cost. The way to amortize this is to multiply all the delta x together, get a final result, and do one inversion. Then you can calculate the delta x, the final delta x you want from this one inversion through this equation. So basically, you achieve the amortized inversion cost. Depends on the number of pairs of additions you batch together. If you batch 100 additions, you get 1 over the 100 amortized cost. Then how do we apply batch addition in bucket accumulation? As I mentioned earlier, you first distribute those points, different buckets, as we show in this figure. Then we figure out how to add the points in the same bucket together. The default or the method used in some other implementations is a tree-based addition. Basically, you build a binary tree of all the points and then use log n times of addition to get the final result. Log n layers of addition to get the final result. The way we implement this is a list-based addition. You need to do more round of additions. Every time you only add the accumulator in the bucket and the top of the list. And you can batch all the additions together because all of them are independent and in parallel. So you can batch the additions from different buckets and achieve a multiplied cost. With this implementation, it's easier to implement than the tree-based addition because you do not need to handle the tree. Also, we achieved constant extra memory usage. because you do not to capture all the buckets at the same time. Actually, you can maintain, for example, we maintain maximum 4K batch size. So as long as we get 4K points in this green area, we can start to do batching instead of waiting for you distribute all the points, including millions of points, into the green area. Then we need to handle the purple area. We maintain a list of this, we call it conflict points. Then we handle them later. So that's the first trick. The other one is the same thing, batch addition in bucket reduction. So if you still remember that equation, here I give an example of bucket reduction of 16 buckets. And there's a visualization here. Like Gregor from ONFs gave us this great visualization. So basically, this equation is basically add all the squares or blocks here. You add this last bucket 15 times, where you add this first bucket 1 time. So you get the square of addition. So how to add them with this batch addition? First of all, you partition those buckets into groups. Here I'm giving an example of group size 4. Then try to, like each of the group are then independent, and we can calculate the additions in parallel. So first of all, we can calculate the sum of each bucket. Then we calculate the sum of the sum. Then in the end of this iteration, you got this yellow area stored in the sum of sum. And then we try to figure out how to calculate the squares. It's done by, like, for each group in the reverse order, you add all the sums. Then you basically get the sum of the width of the right blue squares, basically 4, 4, 4, 4 here. Then you multiply those by 4. You get the area of this square. Then you add all these squares together. You get you add back the yellow triangles with those squares. You get the final addition. Where should we apply the batch addition is here. Because each time this addition is independent and in parallel, you can add them in a batch and achieve a multiplied inversion cost. That's the second important trick. Because of the third one, because of time, I'm not going to all the details of each trick. For the GLV computation, because basically you find a property in the curve where you calculate lambda multiplied by a point. The result is equals to beta and multiplied by the y. Basically, you reduce point multiplication to a field multiplication. That's cheaper. So to apply this trick, you first decompose the 255-bit scala into two 128-bit scalas. So you got half the size of the scala. Then to calculate it fast, the battery reduction is used for faster modular. And with this trick, with this decomposition, you can see this original computation can be transformed to two smaller scalas multiplied by 2 points. P is the original point, while P prime equals to those endomorphism point. That's how the GLV decomposition works, and the result is that you can halve the bucket reduction cost, because you get the same number of additions in the bucket accumulation stage, where you get half of the number of buckets in your bucket reduction stage, so that you get half of the cost. This is the final trick we applied, called the signed bucket indexes. The idea is basically treat the window slice, we call it a slice, in each window as a signed integer, so that you can reduce the value from 0 to half L to minus L over 2 to L over 2, and you get half of the bucket size. That's the final trick. I'll put this online so you can check it later. What's the learnings here? First, we need to really document those tricks, because even if I have the source code available, I have to redigest what the tricks are there. They don't have detailed implementations. However, luckily, all the authors, they gave me a lot of instructions on how this algorithm works on every details. For our implementation, we actually have a per implementation commit, so that you can do regression tests on each of the commits, each of the optimization tricks. You can also study each of the tricks separately. And finally, we have a modular design with unit tests. is like we are on the way to put it in a production-ready track. This is what I want to promote with Open ZK Compute initiative. Thanks to zPrize. I was from the crypto mining world, where the crypto mining is a zero-sum game. People are very incentivized to get a performance edge over the community, over the competitors. So more often than not, we see over 10 times of advantage versus your competitors. Because either as a project, you have you can front run the community because you design the algorithm, you optimize it before others. Or when the community is on CPU, you can use GPU, FPGA, or even build an ASIC. And people are incentivized to not share the knowledge. That's basically what I learned in the crypto community and crypto mining community. But this time in the ZK community, I'd like to, and our company would like to do it in an open way. And after this work, we are going to build an open source Hello 2 GPU acceleration solution. For anyone who is interested in this work, please talk to us. Okay, without further ado, I'd like to introduce you to ArcMSM. It's now fully open sourced. It's available on github.com/snarkify/arcmsm. So feel free to play with it. And if you can come up with more optimizations, just create a PR and start it, of course. And yeah, we are hiring. If you are interested in Nova, Hello 2, GPU acceleration, FPGA stuff, please talk to us. Yeah, thank you.